like.
I mean, it's something that I will use at some point, but you don't need to remember it. I just want to show that it exists. Right. Thanks. Is this okay?
Yeah.
Good. Right, so I was saying last time that we were going to do some counting. And obviously, this counting is going to be to involve the Weyer's counting theorem, Lang-Weyer's counting theorem. So I mean, Lang-Weyer's counting theorem already tells us, gives us an estimate for the number of points of an absolutely irreducible variety. In other words, if Q is sufficiently large, V is absolutely irreducible of dimension D defined on your field FQ, then you know that it will have approximately Q to the D points. And the error will be of the order of Q to the D divided by square root of Q, all right, times a constant. Okay, so of course there are things which are more complicated than just absolutely irreducible variety. And actually, well, the case of quantifier-free, of algebraic sets, okay, is surprisingly, I mean, not surprisingly, but surprisingly difficult. So basically, what is the question? You have a set which is defined by equations, right? So now my equations, they are with coefficients in Z, so they will make sense in any finite field, right? Now you need to find a way of expressing this set, this algebraic set. So let me write it as V of F, right? I need to express it uniformly as a union of things, all right, of V of V1 of F, union V2 of F, union, etc., where the VI of F are absolutely irreducible over my F. And this is all needs to be done totally uniformly, and then I count the number of irreducible components. But this is not so. The point is that they need to be defined over F. So it needs to, okay. Right. So how do I do that? So this is what's called an how do you say, a decomposition intersection procedure. So the aim is that get V1, Vm absolutely irreducible defined over F such that V of F is equal to V1 of F union, etc., union Vm of F. All right. Now, in our case, so if my F is sufficiently big, the fact that they're absolutely irreducible, well, this means that you know how many points they will have, right? Okay. Now, right. So why do you want it? Why do you want these components to be absolutely irreducible? So in general, if you have any field F, all right? And you take an irreducible variety defined over F. Let's call it V. It's not absolutely irreducible. So that means that in some algebraic extension, it decomposes as V1 of F, etc., Vm of F. But these VIs are not defined over F, right? Now, you know that the Zariski closure of V of F is defined over F. That you know, because it's stable under any automorphism of the algebraic closure of F, which fixes F, right? So therefore, the F points have to lie in the intersection of all VIs, right? Of all the absolutely irreducible components of V of F, of V. But then it will have lower dimension than V, because this will be this intersection. Okay.
You took the closure where?
Zariski closure in the algebraic closure. So Zariski closure, I remind you, it's that you have a set of points. It doesn't need to be any set of subset of point S contained in F to the N. And you look at the set of polynomials, with coefficients in F, which in n variables, which vanish in all points, which vanish over all points of S, at all points of S, okay? So you're going to get an ideal of F of x1, xn, all right? Which is prime or not prime. So that's the Zariski closure of my point, of my set S inside F. Okay?
Zoe,
No, to have irreducible thing, you don't need S to be reducible.
No, I meant this argument.
Well, I mean, this is yeah, right, sure. You start with a V, which is irreducible. You look at the components and so on. All right. So in other words, what I'm saying is that if V is not absolutely irreducible, then V of F cannot be Zariski dense in V. Okay. So it's Zariski closure. The Zariski closure of the point of the set V of F will be smaller than V. Okay. All right. Good. So the first thing to do when you have a quantifier-free definable set, so let me see how it works. So if we want to count, we have to do what's called the decomposition intersection procedure. Okay, let me get it. So this was sort of an aside, we'll get back to it. And basically the thing is that we want to prove the following theorem. So this is a theorem that I proved with Van den Dries and McIntyre. I guess my only paper in collaboration with those two people, even though they really counted for me. Let phi of x bar y bar be a formula x bar and n tuple variables y bar and n tuple. Then there is a finite set D, which is contained in 0, 1, n plus q greater than 0, union 0, 0 of pairs B mu and a constant C which depends, of course, on phi, right? Such that for any FQ and A bar in FQ to the M, there is some d mu in D such that the cardinality of the set of points in FQ to the n which satisfy a bar in FQ, which satisfies phi in phi of x a bar in AQ, minus mu q to the d is less than c to the q to the d minus 1/2. All right. So you see that in case the formula phi of x bar a bar defines an absolutely irreducible variety, this is simply Langevin, right? Now, the second thing is that the formula, there is a formula. I guess I forgot to say, I probably should have, yes. And here I also have formulas phi d mu of y bar, formulas for d mu in D, such that, so I don't need to have a formula. So the formula is the formula phi d mu of y bar defines in each FQN the set of B's of A's such that the equality here, the inequality here holds. All right. So I guess one of the components of this phi of d mu, for instance, talking again about absolutely irreducible variety, will say, well, so if the pair is the pair mu d is 1 q to the d, right? 1 d, then I'm going to say if a bar defines, if phi of x bar a bar defines a variety, an absolutely irreducible variety of dimension d. Okay, this is going to be what the formula theta of D1 says. All right. Okay. Well, maybe not quite, but okay. So how are you going to do such a proof? So the thing is first to start with quantifier free formulas, and as I said, and well, if you are trying to count something up to a smaller set, right? You see that you're not really interested in, I mean, you really are interested in sets defined by equations, all right? Because if you delete a small subset, if you are counting the elements of V such that the G of X is different from 0, you are usually taking off a set of much smaller dimension, and therefore which is not going to count when you do when you want to approximate. Okay, I should mention that there are some questions, some open problems to count these things a bit more more precisely, you know, in terms of powers, sums of powers of Q. I should also say that in the case of curves, the constant C of Langevin is explicit. I mean, when it's really it's in function of the genus of the curve. Right. Okay, but we are having just rough estimates. Okay, so before I start on the algebraic case, let me do some remarks. So the pair 0, 0 is there because, well, but I mean, it's not in the original paper, okay, but I'm going to put it because just to say that in case the set is empty. I mean, this just takes care of things asymptotically, okay? It's just easier. I already said that if it defines a variety, then it's Langevin. So I guess one, if phi of x bar a bar defines an algebraic set W, okay, then all of whose absolutely irreducible components are defined over FQ, and if D is the maximum dimension of a component, well, I guess, no, then D is the maximal dimension of a component, and mu is the number of components with that dimension. In other words, the components with lower dimension don't count. But you see, here, there are two things. I mean, I need to, there is a special assumption on W. As we saw before, this is not always the case that all its absolutely irreducible component are defined over FQ. Just we saw the case when W is a irreducible but not absolutely irreducible variety. Okay, so we know how to count it, right? So therefore, it also tells us that when phi is quantifier free, right, then the associated pair, the associated pairs d mu, we always have that mu is an integer. All right. Okay. Another important, yes. Okay. Another important thing is that if Q is sufficiently large, the formula phi of the formula phi d mu of y will define a partition of FQ. All right, obviously, because you cannot have this condition holding for two different pairs. Okay, even if D is the same for the two pairs, you see that if Q is chosen sufficiently big relative to the constant Q and the difference between the two pairs, right, between mu1 and mu2, then voila, then you have a problem. Okay, what else? What's nice? If n equals 1, then there is a number A of phi, right? Such that for any and an R greater than 0, a rational R greater than 0, such that for any Q and A bar in FQ to the M, either cardinality of phi of x A bar is less than A, or it's bigger than, well, I wrote X, I should have written HQ here. A bar is greater than R cubed. So why is this? So greater than, yeah, greater than R cubed. Okay, greater than or equal, whatever. Okay, basically, you see, why is this? It's because the possible values of D are 0 and 1, all right? So when it's for 0, you are going to take, A will be automatically, will have to be bigger than all the mu's which appear in a pair of the form 0 mu, right, in D. And then you have to play with the constant C to increase the A, right? And R will, of course, be the smallest value of mu such that R1 appears in the set D, okay? Or maybe you take R minus an epsilon so that, I mean, I'm not completely sure about the counting, but, you know, you do whatever is necessary so that for Q sufficiently large, if it's not of bounded size, I mean, it will be greater than that, okay? And then you move the A in consequence. But anyway, so what it tells you is that there is a bound and a bound below, okay? If it's not finite, then it has density R, okay, in FQ. Okay, so in particular, that, right, and I guess you could also show that when you are dealing with a pair 0 mu, right, then for Q sufficiently large, the mu will give you the exact number. Okay, because simply C to the minus C times C divided by square root of Q will be smaller than 1. Okay. Okay, so these are good things, and maybe I will tell you the reason why we were looking at those bounds. This was really actually a question of Feldner, which is, can you uniformly define FQ inside FQ square? Right? FQ inside FQ square. Now you see that compared to FQ to Q square, Q is equal to square root of Q square, right? So therefore, it cannot be definable by a formula. Okay. Inside FQ square. I mean, there is no formula which inside every FQ square is going to define FQ, period. No formula of the language of fields. Good. Right, so now we need to start proving this. So as I said, the quantifier-free case, and I guess, maybe this wasn't such a great idea what I did. You see, because you see what I did? That the things I'm going to use, they are there. Okay, so can I erase this?
You can also erase it.
You want me to erase Langdale?
Not the people, just
The theorem. Right. Okay, I'm going to erase Langdale. So, but everybody believes this statement, right? I mean, I guess I'm going to use this. So the aim is I have a algebraic set W. I need to find the irreducible subset, subvarieties of W, which are absolutely reducible, and such that W of F is equal to the union of the F points of those absolutely reducible components. In other words, given W, I need to find the absolutely irreducible component of the Zariski closure of W of F. Okay? They are going to be defined over F. I know that because, well, because that's the way. Because okay, right. Good. So how do we do that? Well, there is this intersection, decomposition intersection procedure. So what do you do? So start with W, okay, which is an algebraic set. Okay. Then you see these results, so they tell you the following things. First of all, there is a constant A, which will tell you, given polynomials of F1, Fm, G of degree less than or equal to D in n variables, right? So the constant depends on n and D. If G is in the ideal generated by F1, Fn, then it's witnessed by polynomials of degree less than or equal to A, all right? Okay. To belong to the ideal is an existential statement, right? I need to find a bound, okay? I mean, you are viewing f of x bar as the union for d in n of the f of x bar less than or equal to d. So like with every such structure, when you have an existential statement, you need to find a bound which only depends on the degree of the parameters, okay? Here, you are looking at the radical of the ideal I, right? So you know that every prime ideal is radical. So in particular, so the radical, I remind you, is the set of G such that some power of G belongs to the ideal, all right? Again, the question is, you need to bound the power, right? So to belong to the radical is an infinite disjunction. If you want it to be first order, you need to bound the degree. And of course, this is bounded here. Incidentally, I could have put G to the B is in I, because if G to the K is in I, then any multiple, if you multiply it by G, it's also going to be I. Okay. Nya, nya, nya. D. D is going to tell you, again, in an effective way, whether your ideal I is prime or not, okay? And again, so it's a question of finding G and H such that the product is in I, but each of the elements is not in I. And this is going to be, can be done, if the ideal is not prime, it's going to be done with some polynomials of degree less than or equal to D. And finally, the E is the most potent one, which says the following. So you have an ideal I. Now you want to decompose it into, okay, I corresponds to an algebraic set, right? You want to decompose it into its absolutely irreducible component, this algebraic set. So in the algebraic closure. No, actually, I don't care. I'm not interested in it. So I have my ideal E, right? Sorry. I'm interested in the minimal prime ideals which contain I. Okay. So we know, what do we know? We know that the radical of I is the intersection of the minimal prime ideals containing I. Right. Okay. So in order to do this, I need to do two things. First of all, I need to find a bound on the degree, okay? And I need to find a bound on the number of such ideals, okay? And in fact, the big theorem is that this bound exists, all right? So in other words, given my ideal I, which is generated by F1, Fn, and can find a finite set of tuples which are going to define minimal prime ideals containing I, right? And such that the intersection of these minimal prime ideals is going to be square root the radical of I. Okay, so let's see how it works. So, okay. So first of all, we start with, we write W equals V1 union Vm, where the Vi are irreducible. Where the Vi are absolutely irreducible over and defined over F, I guess, right. So here I'm using this theorem applied to F-alge, right? So in F-alge, I have this bound works and the degree of the polynomial works. And actually, I guess, yes, right. No, okay. So we can actually find parameters for those VIs in F-alge, okay? Fine. So we work in F-alge. Then, so the number, well, let me call, is it M or is M already taken for something? No, it's not taken. No, whatever. So we know that M is bounded. So if all VIs are defined over F, this is fine. Okay. If not, we replace so first we may assume, so we group those VIs in terms of conjugate. If not, so we may assume W is irreducible. Maybe I should have done that first, right? Maybe I should have first decomposed W into F irreducible components, okay? And then, okay, is irreducible over F. And then say, okay, if they are not, if it's not absolutely irreducible, then I have to do something. Right. So then what's happening is that from this W, we get that the V1 Vm are the absolutely irreducible components of W. So therefore, now you look at the new variety, which is W prime, which is V1 intersect Vm, and you start again. Start the same procedure. So now we know, so you see these V1 Vm will be generated by how do you say?
Zoe,
Polynomials with coefficient in F-alge.
can you explain why this is not empty even? Or is it obvious?
It could be empty.
Oh, okay.
Could be empty. Doesn't matter. It's smaller than W, that's for sure. Yes. So what I should say is that you know that, okay, you are going to tell me, how do you know that there is a bound on the degree of the extension in which these guys have their coefficients? Do you have any idea why?
you maybe just say before that? I mean, why do we need this bound? I mean, I don't understand what's the connection to what we're trying to do.
Okay,
I'm missing that.
I want to count, I have a W, right? I want to count the number of irreducible components of the Zariski closure of W of F. Okay? So first step, I guess.
Because we use the number of components you needed.
Right. So let's say first step, I decompose it in irreducible components. Okay. So now it suffices to count what's happening on the number of points on each irreducible component. Okay. Now, if VI is absolutely irreducible, so if VI absolutely irreducible, then it's okay, right? Because I use Langevin. If not, well, I need to do something. So if not, so I'm going to choose one of them. So we may assume W is irreducible over F, and then we want to know what are the absolutely irreducible components of W and take their intersection. Okay, that's what we want to do. Yeah, I didn't do it quite right. All right.
And you're using this because you want it to be uniform in the field.
Yes, that's right. I want it to be uniform in the field. So what's happening is that, first of all, how many components are there at most? They're at most E, right? So now I'm working over, my W is irreducible over F. So there are at most E, absolutely irreducible component. Okay.
F bar then in your statement E, because that's not about the absolutely irreducible components. That seems to be the irreducible components.
I'm working in F-Alge. I'm working in F-Alge. I mean, this thing works in any field. So it will be the same. E will work for F and for F-Alge. Okay. My I here, I'm applying it to the set of to the ideal generated by the polynomials defining W, which is a prime ideal, okay? But it doesn't matter. I mean, it's a prime ideal in F, but it's not in F tilde. Okay, not in F-Alge. All right. So in F-Alge, I know that there are at most E irreducible, absolutely irreducible components. We also know that they are all conjugates over F, sorry. Therefore, they are defined over an extension of F of degree at most E. Is it less than or equal to E? Yeah, I guess it's less than or equal to E. And any element will have less than or equal to E conjugate. Every tuple will have less than or equal to E the conjugates. Okay, but now you see that with the help of some parameters, now I'm back to F. Okay, I can interpret in F extensions of Galois extensions of degree less than or equal to E. All right. So I'm going to say, well, there is a Galois extension of f of degree less than or equal to e. So this is a statement about the coefficients of some minimal polynomial defining that Galois extension. And in that Galois extension, there are the ideals generate I find the coefficients of the E minimal prime ideals containing I. All right. All right. So let's call this Galois extension L of F. So now I'm working in the pair, if you want, LF, which is interpretable in F. So this L depends on certain parameters, which are in F, but it's uniform in the degree of the parameters. And what's happening there is that I'm going to look at the intersection of all irreducible components. And working in L, working in this extension, working in L, I know that I can find a set of generators using all these things, okay? Because now you see that the intersection of those will be defined by all the conjugate of a defined set for one of the components, okay? So, right. And eventually, so you are going to get now the intersection of all these absolutely irreducible components is defined over F. Might not be reducible. Have to repeat the procedure. Okay. All right. So it's a bit boring, this thing. I mean, it's not, and I guess I was not completely convincing, I suppose. I mean, I was a bit waving my hands, but you see that with some work it can be done and some care. You also see that the bounds are absolutely awful. Yes.
What is the end of the, I don't understand how you finish from this. You do the intersection.
Now you finish when it becomes finite. I mean, when it stabilizes.
And then how do you go back?
Okay, as I said, if VI is absolutely reducible, then you are finished with that component, okay? All right? The first step, you look at the F irreducible component. You test whether they're absolutely reducible or not. If they're absolutely reducible, you leave them. If they are not absolutely reducible, then you start a decomposition procedure, okay? So in other words, you see the point is that the F points of W, the F points of W, right? It will be equal to the F points of the intersection of all irreducible components, okay? So now you work with that, all right? So when does it stop? Well, it stops when all the algebraic sets which appear in all the irreducible algebraic set which appear in your decomposition are absolutely irreducible.
So the question asked before whether this intersection is empty. No, it's not empty. It contains the points of W.
Well, if W of F is not empty, it's
yes.
going to be not empty. Yes.
And if it's not an algebraic set, it's called the general form.
Okay, the point is that when you work in F-alg, no, it is an algebraic set. You see, the thing is that
I'm saying the theorem is about the general formula.
Yes, okay. And at the moment, I was trying to do the algebraic sets.
Okay, I thought you finished.
Okay, so because this is sort of the start with W algebraic set. Yeah. Okay. So now, okay, as I was saying before, if you delete from an algebraic set a Zariski closed subset, right, you're not going to change anything, right? I mean, as long as the dimension is less big, right? So, I mean, we consider this thing as finished, all right? I mean, I consider it as finished. Is it okay with you? Okay.
Yeah,
so,
yeah, it's fine.
Yeah, no, I'm joking.
Okay.
Right. Yes. So then, okay, now I can hide this again. What are we doing? So now we have quantifiers.
This is 25.
Now we have quantifiers. what do we do with quantifiers? So first, so I don't know if you remember, but last time I said that every definable set, every definable set is the projection, the finite to one, projection of an algebraic set. Now, the thing is, right, so here I'm going to lie a bit, all right, because the, how do you say, the algebraic set actually needs additional parameters, all right? Remember those functions C, those constants C? Well, I guess, we can work also in the language LC. I mean, we have the same kind of results, right? I mean, the constant C, the only thing, remember the only thing they had to satisfy was that the constants at level n had to be the coefficients of the minimal polynomial of some guy of degree n, right? So it's sort of, there is nothing else you know about the C's, you don't really care. Okay, so the C's will be involved in the definition of this new algebraic set, okay? But there is a projection pi from W of F to this set, the set defined by phi of F A bar. Right? Let's say we are working in a pseudo-finite field again.
Alpha phi will be bounded.
And the size of the fiber is, of course, bounded. Finite to one, yes, the bounded fiber size. Okay. Yeah, because this is uniform, so the size has to be bounded. Okay. All right. So how do we do this? So indeed, right, so we have this bounded by some n. So this W is defined by polynomials, right? I mean, it's an algebraic set, right? Okay, so we know how to count its points. So we should be able to count the points here. So basically, the problem comes down to, given if V contained in W is absolutely reducible, count the number of points of pi of V of F. All right. Now the problem is that pi of V of F, well, it's not V of F, right? It's going to be something in function of V of F, right? Which depends, of course, on cardinality of V of F, okay? So this means that if V had dimension D, its the projection will have size roughly Q, I mean, a constant times Q to the D, maybe, right? So it might depend, right? Okay, good. Now what? Well, if all fibers have size E, then what? Then cardinality of P of V of F is equal to 1 over E cardinality of your F. Am I stating the obvious here? All right, but okay, they might not have all the same cardinalities, right? So what do? Well, you are going to partition pi of V of F in subsets where they have a definable subset, quantify a free definable subset, or well, almost quantify a free definable subset, but no, subsets where depending on the size of the fibers. Okay, so it's a bit messy. The computation is a bit messy. Basically, the idea is the following. If you have, let's say, if you have 2 points, if you have at least 2 points over a given pi of a bar, right? This means that there is a point in the variety which is obtained by taking the tensor product via pi over v. So in other words, the points of this are going to be things of the form z1, z2, x, where z1, z2, where z1, each of z1 and z2 are in v cross in w cross w, and pi of z1 equals pi of z2. Okay, these kinds of things. So you can find and you can notice that this is I mean, it's just defined. You know, each z1 and each z2 is defined by the saying that, and then you are going to look at the Zariski open subset, which says that z1 is different from z2. Okay, so this will tell you you have at least 2 points. Okay, but you might have 3 or 4 or 5 or 6 and so on. So you do the same kind of trick for all integers, then you know you're going to stop at n, right? And you count and you do some computation and you get a rational number. Okay. Okay, good.
Why did you need V to be irreducible? We already dealt with the general algebraic case, no?
I'm saying it's irreducible.
No, but why did you you start with W? Why did you go to V? Why didn't you just stay with W? That's my question.
Did I make a mistake in my?
No, I don't know. I'm just asking. You started with W and then you went to some absolutely.
Right. No, I'm just saying we can assume that. Okay, I reduced to the case where W is irreducible, if you prefer. Absolutely irreducible. Okay. I mean, it suffices to count on each. I mean, we have W of F. We can assume by the procedure we did before that it's a union of absolutely irreducible sets, okay, which are defined over F. All right?
Oh, okay.
By what we did before. Okay, so it suffices to count on each of those absolutely irreducible component of maximal, right? Maximal dimension. And so that's why I went to a V, that's all. That was just the thing, okay? Did I say something? No, right, sorry. I messed up. No, you're right, it's not my, sorry. That's what I wanted to come over. Yeah, sorry. Thank you, Itai. That's what I wanted to consider, right? Yeah, it's here. It's here. Sorry. Good. So here we are. So this tells you, you see, this whole procedure is sufficiently uniform that you can define the second statement, which was saying, I can define the set of A bars such that the inequality holds, is going to be correct, right? I mean, it follows from the proof because it's so uniform. So this is not a problem. Maybe I should stop, right? It's 5 minutes break. I mean, it's a good point. And then I tell you some of the what do you say, the consequences of all this. So 5-minute breaks. Ah, yes. What do you want to erase? Let's leave this, and the others can go, I suppose. All right. J'ai oublié mon masque. It's so, I forgot my mask. It's so easy to forget one's mask. Alors en France, il commence à serrer la vis.
Ah ouais?
Ouais.
Ça, je n'ai pas suivi. Qu'est-ce qui se passe?
Les chiffres ils montent, ils montent. On en est à peu près à 30 000 cas par jour maintenant. On suit de près les Allemands. Voilà. À partir du 1er décembre, tout le monde sera éligible à la 3e dose. Etc. Tu vas aller voir tes parents?
Je vais essayer, ouais. Je me suis pas remarqué aux États-Unis. C'est un peu compliqué. Je devrais pouvoir rentrer en France et revenir ici simplement.
J'ai ici pour toute l'année aussi. Ouais. Et tu pars quand ici, toi?
Tu veux dire pour les vacances?
Oui.
Je ne sais pas encore, je n'ai pas encore fait.
Tu restes pour la dernière workshop ou pas?
Oui, je reste jusqu'à la fin.
Justement, normalement, je pars le 11, mais je suis en train de me demander si je ne vais pas rester un peu plus.
Un peu plus?
Oui.
Ouais.
Bon, comme ça, pour être là la dernière semaine, tout le monde pleure en se disant au revoir, etc. Donc, je ne sais pas. Mais il faut que je réfléchisse parce que ça va me coûter de l'argent quand même.
Ah, c'est sûr.
Ben oui, parce que changer mon billet, voilà. Et les billets, près de... Enfin, c'est cher, quoi. Ah. All right. Okay, so I'm going to give you some application of these things. I mean, they are funny things. I mean, it's it's not anything particularly profound, but it's nice. I guess so. One of the things. So the first thing, as I had noticed, as I had already mentioned it, right, is that there is no formula which defines FQ in each FQ square. Okay, simply because a formula, a binary formula, is the set of solution is going to be either a multiple of Q square or bounded, okay, bounded size, as we said. But moreover, you can say that one cannot uniformly interpret FQ square, FQ in FQ square. Okay, so interpret means, well, interpret means interpret, right? I mean, so you take some Cartesian power of FQ square, and you take definable equivalence relation on that, and it should be FQ. Well, if you think a bit about it, right, each of the equivalence class, right, will have size, which is a multiple of some power of Q square, all right? So in the end, you get that, well, the definable set modulo I mean, it cannot have size a multiple of Q. That's what I've said. It will always say a multiple of a power of Q square. Okay? Such a thing. So that's one thing. So there were other funny things. For instance, there is no formula.
Zoe, regarding two, I didn't really understand the proof, but is it even more that you cannot even have an equivalence relation with Q classes?
Well, I mean, you can have an equivalence relation with Q size, but most of them will have, one of them will have maximum size or something. I mean.
So the point is all the classes have the same size? That was the point? Or?
Yeah, I mean, well, I guess maybe I didn't say. Okay, so one can prove it. That's what I'm saying. Okay, yeah, I guess the reason what I said was not totally correct. There is no formula which defines in each FQ the set of generators of multiplicative generators. Okay, this is simply because actually, okay, there are some FQs in which, so you remember that FQ cross is cyclic of order Q minus 1, right? So first of all, and you know exactly what are the generators, right? In general, when you have so let's say if you have a group which is, if you have a group which Z mod ln Z, right? Well, what are the generators? It's the guys who are congruent, who are not in ln minus 1Z, right? So how many of them are there? Well, you have, so it's Euler function. I mean, it's really Euler functions, right? Euler function. So, I mean, if you look at the set of generator of L of nz, okay, the multiplicative generators, this will be what? This will be, sorry.
Not the number of generators.
Generators of.
Okay.
No. You how many of them do you have? You have L minus 1, L to the N minus 1, if I'm not mistaken. Yeah, that's right. But you see that, so it's the Euler function. Then when you take the product of such a thing, so I mean, this is the proportion, right? So in other words, if you look at, I mean, if you look at the proportion of the generators over the cardinality, you are going to get something that N minus 1 over N, right? Over the cardinality of that set, which is equivalent to that, right? Now you see that if you have many primes which occur in the decomposition of Q minus 1, well, you have many products of this form. And they go, you know, if you have too many of them, well, it becomes very small very quickly, all right? And in particular, there is no lower bound, all right? So that's it. So that's the proof. Yeah, okay, 2 definitely needs more work than what I just said, right? Okay, so another interest of this is that, so what does this say? It says that basically you can count the number of points uniformly. So what does it say about a pseudo-finite field? Well, you see, it says, okay, let me tell you what it says. So applications to pseudo-finite fields. So of course, there is no question about counting points in pseudo-finite fields since they are infinite, right? However, the formulas phi d mu, they still, I mean, the pairs, set of pairs d mu and the formulas phi d mu make sense. And so given the formula phi of x bar, y bar, a pseudo-finite field F there is a unique pair d mu which belongs to this set D, which was D of phi, right? And this set D depends on phi, of course, right? Such that, and given a tuple A bar in Fn, there is a unique pair D mu such that F satisfies phi D mu of A bar. Okay, so what does it say? It says that if F was finite, I would count more or less the number of points, right? However, F is not finite, but F embeds elementarily in an ultra product of finite fields. And there it says something, right? There it tells you that for almost all the fields in the sense of the ultra product, right? We have more or less mu q to the d points, right? For that mu and that d. So first of all, so this means that d corresponds to the dimension of the Zariski closure of the set defined by phi of f A bar in F, right? What does mu correspond to? Well, at this moment, we don't know too much. But if d equals n, what does it correspond to? If d equals n, so that means that, I mean, my phi of fn, my phi of f A bar is really quite big, right? It's of dimension, I mean, generically, all points are in satisfies phi, right? Or at least many points satisfied. I shouldn't say all, because you know the complement might also be of dimension n, right? But the complement might also be Zariski. That's what I'm saying, right? But if you look at what happens on each of the finite fields, well, the mu gives you the proportion of points which are in there. So mu gives a measure, gives the proportion of points which are in phi. Okay, so you in phi of FA bar. So you see that without saying so, what I'm just telling you is that actually there is a measure on the definable subset of F to the n, right? So you have those which are Zariski dense and which have associated dimension greater n, right? And those, and so whose measure will be positive, would be that mu, the mu. And then you have those which have associated dimension less than n, and those will have measure 0, okay? Relative dimension. So, well, one just does that more uniformly for any set. So what this means is that given a definable subset S of Fn with associated number pair V mu, one defines a measure mu S on definable subset of S simply, so if D contained in S, not D, S prime contained in S has associated pair in mu, we define mu S of S prime will be equal to 0 if E is less than D and equal to mu over mu if E equals to D. All right. And so you verify this measure. You see it's a sort of non-standard counting measure. So you verify, of course, that it's additive. It satisfies Pubini. When you have a map from one definable set onto another, and you know that all fibers have a certain size, then you know exactly what the size of the image will be, what the relation between the sizes will be, and so on and so on. So this is really quite a good thing.
Generally, it's not necessarily a probability measure or something. I mean, it could be that you have more components when you go.
Doesn't matter.
No, that's a question. Not.
No, yeah, right. I mean, no, I'm just saying that this is a nice counting measure. That's all. That's all I'm saying, really. That's all I'm saying. Okay, so right, what can I tell you too? Right, so I guess there was the question of whether this measure could, there were other measures which were nice on PAC fields. Well, I guess, okay. So first of all, this type of result led to people whose name I forgot now. I know that Dugald was involved and probably Charlie Steinhorn. So Dugald Macpherson, Charlie Steinhorn, and probably other people too. But to define the concept of, the general concept of measurable structures and of asymptotic classes, and to sort of generalize the results to that setup. I should also mention that in the case of, okay, so here I'm going to say something very vague, but in the case of ACFA, so using the counting results of Udi Hrushevsky on sets of on sets of how do you say, of finite order, okay, meaning that, well, okay, I'm saying this for the specialist. There are results also of Wrighton and Tomasic, counting number of points and therefore defining measures and stuff like that. Okay. All right. What else should I tell you? So this certainly was developed, and one. Okay, as with finite fields, pseudo-finite field, I'm going to show you in a moment. Well, I'm not going to show it to you, but it turns out that indeed that their theory is simple, and not only simple, but super simple. And this is due mostly to Udi Hruszowski. What happens is that you can define. So what is a simple theory? It's a theory in which you have a good notion of independence, all right? A notion which is, okay, invariant under isomorphism, symmetric, which is sort of two sets are independent over a third one, if and only if it's true for any finite subset of the two upper sets. You have some things of transitivity and so on. Okay, so it behaves nicely. And the last condition is that it satisfies the so-called independence theorem. All right. Now, okay, it turns out that algebraic independence is actually the notion of independence which works in pseudo-finite fields. So what is algebraic independence? Well, you're going to say that A and B are independent over C. This means, so algebraically independent, this means that the transcendence degree of, let's say C is a field, transcendence degree of C of A over C is equal to the transcendence degree of C of AB over C of B. Okay? This is a notion of algebraic transcendence, algebraic independence. You notice that it is just independence in the sense of ACF, right? So it satisfies all the good properties that you can imagine, right? The transitivity, symmetry, blah, 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 the fact that you don't only need finitely many elements to realize that something is not independent and stuff like this. The difficulty in our case is because of the F is not algebraically closed, is to prove this independence theorem, okay? It actually is not as bad as it sounds, but okay, it needs a proof, definitely. There are, however, other consequences of this measure which can show that certain formulas are stable, and you know that things behave. They give easily some how do you call it? Some stability, some results with a stability theoretic flavor. So the one result is the following. So you have a formula phi of x bar y bar. You have a field F. And what it is that there is no infinite decreasing sequence of A bar I. And what's the reason for that? Is simply because for each of these AI bar is going to satisfy one of those phi d mu one of those finitely magnified in mu, right? So you quickly reduce to the case where they all satisfy the same, okay? So we have a strictly descending chain, but you see that it's not going to work. I mean, it's because of the measure, it just cannot work, okay? Because you see, I mean, what it boils down to is that inside a definable set, you cannot have a strictly decreasing subsequence of things with measure 1. Because what would be the intersection? Okay, what would happen to the intersection? Yes, I guess so. The proof I wrote in my notes is a bit different. So it's first of all, in the case where the dimension is 0, it's clear, right? So we assume they all have the same. We assume d mu all AI satisfy d mu. So if d equals 0, then this is clear. So we want to show no strictly decreasing. And if not, then this means that when you look at phi of f a0 minus phi of f ai, this is a strictly increasing sequence of sets of dimension less than d. Right? D minus 1. Okay, so I guess, right. Yes, the strict, right, no. There is no infinite strict chain. So this is not the order property, not the strict order property, sorry. So I guess here my I would be in Z. Okay. So if I equals 0, if d equals 0, there is no infinite sequence. I mean, so you need to do two things, right? There is no infinite strictly descending sequence, and there is no strictly ascending sequence. When d equals 0, this is sort of clear, and then you have the induction step. All right, so that's one thing. And then there is also the Shelar rank, which is the following. And this will use the relative measure, is that given phi of xy, there is a number m such that in any field f, in any pseudo-finite field, f, if S contained in Fn is definable, and AI I is such that dimension of phi of f ai bar is equal to the dimension of S. By dimension of S, I mean the dimension of the Zariski closure of S. All right. And for I different from J, the dimension and phi of F bar contained in S, right? Dimension of phi of F ai bar intersect with phi of F aj bar and is less than D, then I is finite. And you see that it follows immediately from the fact that we have a measure. So we look at the measure mu s, all right? Mu s of FAI is going to be positive for every I, right? It's going to be positive. We know that it's going to be one of finitely many numbers, right? So in particular, it's going to be bounded below, all right?
The dimension is that the associated D? Or?
It's the associated D. Yes, as I said, the D corresponds to the Zariski closure, okay? To the dimension of the Zariski closure. So the point is that mu S of phi of X ai bar is bounded below. Okay? Now, the fact that when I take the intersection of two such sets, I get something of measure 0, right? Right? So clearly, I cannot have that a set of measure 1 contains an infinite set of subsets of positive measure which are almost disjoint, right? That's all. So this M, you see that the M, in fact, really, well, I guess it might depend a bit on S. I mean, you could imagine that S has.
You said I is bounded by M.
Yeah, right. I guess this M depends, M equals M of S. Okay. So M of phi and S. So if S define, okay, so M of phi psi, where psi is defined by psi, okay?
No, I think you were saying that M is not in the conclusion.
But it's the bound on the size of I.
Right?
Yeah, yeah. Oh, it's not, then I is finite of phi is less than or equal to 1.
And then you could do the same thing for, or maybe this already follows, but you could do the same thing for like K, like the intersection of any K.
Sure.
Jobs.
Sure. I mean, this is just a counting thing. So you see, for instance, right. Right, so I guess you see, I wanted the M to be uniform. So then if they want the M to be uniform, then it has to depend, of course, on the S, because if you take, okay. So it's M of phi psi. In any case, whenever something is defined, there is a bound, okay? And so this, for instance, has applications when you look at groups. So let's say you have a group which is definable in your pseudo-finite field, and you want to, so you have a definable subgroup. G, a group definable in F to the finite, right? H, a definable subgroup of G. Then you have that mu G of H is greater than 0 if and only if the index of G in H is finite. Obviously, right? Because G is the union of all the cosets of H in G, right? So if there are infinitely many, well, they all have the same dimension. It cannot be that that dimension is D. And so this is, of course, the same as dimension of H. Okay. Now, what else can you do? There was one thing which was very nice, which is that suppose that let F from G to H be definable. We assume that okay, no, sorry. I shouldn't say that. I'm not quite ready yet to say that. So there is the notion of algebraic groups. You all know what an algebraic group is. It's a group, algebraic group G, so it's a group which is defined. So when in the affine case, it's just defined by, let's say if it's a subgroup of the affine plane, affine space in n coordinates. So it's just something which is defined by polynomial equations, right? It's an affine variety in the sense that I've been using, and with a group law, which is defined by rational functions or something, okay? So you know what it is. I mean, example, for instance, GLN of K, or the multiplicative group of K, or the additive group of K, things like that. You also have projective versions of these, like for instance, elliptic curve, you must have heard of these things, but also abelian varieties and stuff like that. So, I mean, there is a whole thing. The important point is that these things are definable without quantifier. They are definable in ACF, right? As is the group law, and doesn't, right? Okay. So it's but basically quantify free definable, okay, and lives either in some affine space or in some projective space, okay. Now you have the notion of, so as a variety, there is a notion of irreducible component, okay? And it turns out that your general algebraic group has finitely many irreducible components. So by irreducible, I mean absolutely irreducible component. And if G is defined over F, then G0, which is the component containing the identity, of the group G, is defined over F as well. Okay? And in fact, and in that case, you have that G0 of F is Zariski dense in F, in G0. All right? Okay, so why is this latter condition true? So provided if F is PSC, sorry.
Without the just mean algebraic closure?
I'm sorry.
When you just write G0, you mean what?
I mean
Without
the absolutely irreducible component of G.
No, I'm sorry. I meant when you write G0 without G, it's just the point in the algebraic closure. You mean what do you mean without the parentheses?
Okay, I'm talking about a variety which has certain which has irreducible components defined over Fh.
Yeah.
What I'm saying is that one of those components is actually the one which contains the identity is actually defined over F. That's all I'm saying.
But when you think G0 of F is Zariski dense in G0, you mean in G0 of F arg?
Yeah, for instance, if you want.
Okay.
What no, but Zariski dense has sense whatever. It says it does not satisfy any more polynomials than the one defined in G0. That's what it says, okay? That's what Zariski dense means, right? Okay, so let me write this again because I guess this is not totally obvious to some of you. So I mean, this is sort of baby algebraic geometry, but you know, I guess, well, one needs to know it. So you have V, an algebraic set, and you look at I of V, so contained in Fn, let's say. V an algebraic set. No, sorry.
What I'm saying G0 is definable F, so there's some ambiguity in what it says. I mean, you can take the dense.
Okay, V an algebraic set defined over F. S contained in V is Zariski dense by, so this is defined by an ideal I contained in F of something, right? Which is absolutely irreducible. Well, actually, I don't even need that. I mean, I certainly, I would need at least that the I square root of I is irreducible, is, okay? So S contained in V is Zariski dense, if and only if you look at the set of polynomials with coefficients in F, right? So this is contained in F of X bar, this is equal to I. All right? So what I'm saying is that here, I'm saying that the G0 has a definable ideal, has a defining ideal, which has its with polynomials which lie in F, okay? So the I has its coefficients in F. And now I'm looking at the F points of G0. I mean, in general, over any field, right? It's not clear that G0 of F is dense. I mean, if you have a variety defined over a field, even if it's irreducible, it's not clear that V of F is Zariski dense in V, right? Because V of F might be empty. You're not saying anything, right? So this is saying the fact that it's Zariski dense in G0, this is says that not only it has points, but it has dense in many points, okay? But you cannot distinguish, you cannot cut it out by a smaller subvariety, okay? And in fact, this is true. So if F is PSC, this is always true. And let me give you a proof. Fine. Oh, sorry. Okay, so let's bag it. So okay, the thing I wanted to say is that if F from, because it's a nice result, if F from H to G is an ecomorphism of algebraic groups defined over F, F being pseudo-finite. So epimorphism means that in the algebraic closure, it's going to be on 2. and you assume that H and G are connected. So H equals H0, G equals G0. Then, and if care of F is finite, then you actually have that the index of H of F, of G of F inside, of G of F, the index of H of F of H of F inside G of F is exactly the size of the kernel of F points of the kernel of F. And why is this true? It's because it's true for finite fields. Okay. All right. So sorry, I went over. I'm sorry. So next session will be 2 weeks at 2:15, I think, because Udi Hrushevsky will have the Coxeter lectures. So sorry about going over.